Hello and welcome to our talk titled Routopsy, where we'll discuss modern routing protocol vulnerability analysis and exploitation. I'm Szymon Żukowski. I've been hacking at corporate networks for over 3 years. Before that, I was a student at University of Pretoria. I enjoy application security and writing code. You can catch me on Twitter at @thegoatfarmer.
Hi everybody, my name is Tyron Kemp. I have roughly 4 years of networking and network security experience. I'm working towards 3 years of pen testing experience. My Twitter handle is tkemphacks. I don't really know how Twitter works or any application for that matter. I enjoy hacking infrastructure. Myself and Simon are both security analysts at Orange Cyber Defense. We're part of the SensePost team. We want to become your neighbor. And what we mean by that is we want to show you how to identify some cool vulnerabilities using Wireshark, how our initial attempts looked at performing these exploits on these vulnerable protocols, what are the impacts of these exploitations, and some of the challenges that we face or you may face in attacking these protocols. And then finally, how our toolkit attempts to address some of these challenges. So we went on some pen tests, and on reoccurring occasions, we saw these dynamic routing protocols and first hop redundancy protocols being bled into sort of a user network space. So in our toolkit, we'd like to include a bunch of network-related attacks, but for now, we're focusing on these two classes, and they are similar in the way that you can manipulate traffic flows, but for now, understand that dynamic routing protocols route traffic between multiple networks, whereas a first hop redundancy protocol is more of a high availability mechanism. So there's a lot of acronyms and jargon and alphabet soup going to be thrown at you. Please try and stay with us. For some of the FHRP sounds similar to the DRP, so it gets confusing, but in the DRP stack, we're going to focus on EIGRP and OSPF, and the FHRP stack, we're going to focus on HSRP during this talk. So why are we doing this? Like I said, on multiple pen tests, we saw these things being bled into different networks, and we're not finding these vulnerabilities in certain topologies or bound to a certain industry. We're seeing them in a bunch of different corporate networks, being it ISPs, being it banks, being it smaller type of networks. We're really seeing them all over the show. Additionally, these dynamic routing protocols are being used in Kubernetes. Kubernetes makes use of container network interfaces, or often referred to as CNIs. And for example, you get a CNI called Romana, which makes use of OSPF, and then there's another one called Calico, which makes use of BGP. So we're going to give you a little bit of a background on what the purposes of a DRP and a FHRP is. But before we do that, let's explain what a static route is. So if I want to route from the 10 network to the 40 network, I need to add a route from router A to router B, and from router B to router C. And then you need to take care of the return path as well. So you need to add a route back from router C to router B, and router B to router A. So that's quite tedious, just explaining like static routing between three little routers. So now imagine yourself in this large corporate network with 100 routers and 1,000 different networks, and now you need to configure all these static routes indicated by the blue arrows on the slide. And then you probably need to take care of some high availability as well. So you need to go configure extra static routes with different metrics and priorities to ensure that you can have failover or high availability in your network. So that's not really a scalable solution. So that's why we have dynamic routing protocols. So instead of configuring these bunch of static routes, you can configure a protocol like OSPF or EIGRP or RIP, etc., on your router, and it will become a neighbor with its adjacent router. And the neighboring concept is something that we will refer to throughout the talk. So once you configure these protocols on the routers, it will take care of automatically sharing the network information, and it will also take care of the automatic failover if a link were to drop. In terms of first hop redundancy protocols, there's sort of a logical group created between an active and a standby group. A virtual MAC address is assigned to this logical grouping, and should the active device fail over, then the new active appointed router will respond to this virtual MAC address. So there might be a network failure, but it would be transparent to the user, and the traffic would just flow as expected. So Simon, don't you want to show us where you can find these vulnerabilities or how to look for them?
Yeah. So how can we look for it? Well, let's open up a packet capture, for instance, Wireshark, And if we take a look at the very first packet we've captured, it's an EIGRP hello packet, right? And so when we've got these packets coming in, there are certain fields we want to look out for because we need these same values for our router if we would like to neighbor up or perform an attack. In the case of EIGRP, the very first thing that we want to take note of is the autonomous system number. In this case, it's 100, so we would have to configure our router to have the same autonomous system number so we can neighbor up with the router 192.168.100.1. Now you'll notice that in that packet capture, there was no authentication. And so we can perform a very simple or easy to do attack. We don't have to worry about that. But Taran, what if there was authentication?
Well, there's two variants of this. So either it would be plain text or it would be hashed. And if it's plain text, we'd do exactly the same thing. You'd look at the packet capture, you'd extract the plain text password and include that into your sort of attacker config. But what would happen if it were hashed or there was some crypto applied?
So if there was some crypto applied, we would then take that packet capture and we could run it through something like ettercap, which would parse these packets and then form, or rather create, a hash from that data that can be then supplied into a password cracker, for example, John the Ripper. Take a good word list and you may be able to crack it. Once you've cracked that password, you can configure your router with this new password and now it can attempt to neighbor up. So let's take a look at a packet with password and specifically crypto. So if we have a look over here, this is an EIGRP hello packet, and if we take note, over there is now an authentication MD5. And it's got various bits of data which we won't easily understand, but something like ettercap would be able to easily take this data, create the right hash, and then we can supply that to a password cracker like John the Ripper. Now let's take a look at OSPF. That's another dynamic routing protocol. And in here, there are different other fields that we need to take note of. In this case, the first field is the area ID. Then we notice that there's authentication, but this is of type simple password or clear text. And so we won't have to involve something like ettercap to extract it and crack it. We can easily observe the clear text password and then use that in our router. We then take note of the hello interval and the dead interval. And that's pretty much it for OSPF. Now when we look at something like HSRP, which is a first hop redundancy protocol, there are a few things to take note of, but first we need to make sure that we're looking at packets with the active state. Because this is important for us to carry out the attack, we need to make sure our priority is much higher than that of the active router. Then we take note of the hello and the hold time, which are 3 and 10 seconds, the default values. And then we can see the priority value for this specific router or default gateway, which is also active, is 150. And so our priority, if we would want to attack this protocol, has to be much higher than that. If we then look at the group number, we also need to get this right. So we form part of the logical grouping we would like to attack. You can also see that there is authentication data. And in this case, as a default Cisco, by default, these are configured with Cisco and in clear text. And lastly is the virtual IP address. This is the IP address that the users on the current network are configured with as the default gateway. So how do these issues creep into a network? Well, one such way would be through minimal configuration. If we take a look at router 1 and its configuration for OSPF, there is a network statement that is very wide. And this basically means that OSPF hello packets would bleed out to all the networks of this connected to the interfaces of this router. If we take a look at the second OSPF configuration on router number R2, there's two network statements in here, a bit more specific, but still a bit too overbroad. Networks interfaces connected to the networks of 192.168.10/24 and 192.168.20/25 would have then OSPF packets bleed out to them. Now, let's take a look at Kubernetes. So in Kubernetes, Taran mentioned there are CNIs, and one such CNI is Romana. Romana allows us to configure OSPF within this cluster. Say we would like to join this cluster, or rather share dynamic routing information between a cluster and your traditional network. Well, so the person that's typically configuring a Kubernetes cluster is a person of a DevOps background and not necessarily a network engineer. And in there, they may have also some issues trying to configure Romano on a cluster where there are multiple OSs used. And because OSs sometimes have different naming schemes for interfaces, they may not know what the interfaces of all of the nodes are. So they may use a wildcard, which would then lead to OSPF bleeding to all the networks that the nodes are attached to. Tyron, where would you find this on a network?
Simon, that's a really good question, but before we go into that, I just want to reiterate that we sort of have a rudimentary understanding of where these protocols fit into the network, and that we've shown how to identify them. The process is similar. You open up the capture, you look at the multicast packets, and you apply your config according to that. But let's consider ourselves connected to the access layer, the switches denoted in the slides, and which protocols are we likely to find in that layer? You're likely to find something like HSRP providing you with a default gateway. However, if you find yourself in a network, or you've pivoted to a network where you have layer 2 connectivity to a router or a firewall, you're likely to find a dynamic routing protocol because these appliances support such protocols. Other than that, firewalls and routers often make use of VRRP to achieve high availability. So if configured insecurely or incorrectly, that could bleed into that local segment as well. Other than that, we mentioned Kubernetes using their CNIs, and they support DRPs. So if you were able to influence routing within Kubernetes, that may bleed into or propagate into the traditional network and vice versa. So what's the impact of these type of attacks? Well, consider yourself the red workstation on the slide. You've connected to a LAN, and you have knowledge of the computers in your sort of LAN segment, and you have a default route pointing to your default gateway, but you haven't learned anything yet. You start interfacing with the default routing protocol, and you learn of these new networks. You learn of the finance, and you learn of the server network. So you've literally just neighbored up with the routing protocol. You haven't done anything malicious as of yet, but the benefit of this is, from an attacker's perspective, you don't have to go and nmap big/16s or masscan or whichever tool you prefer using. You've learned exactly which networks are active within this organization. So it's sort of cool in terms of enumeration. You have a lot more accurate description of what's going on, and you can pinpoint your attacks a little bit better. So that's cool. You can neighbor up, but can we take it further? Yes, we can take it further. So consider the traffic flow indicated by the blue arrows, sort of a normal traffic flow of a user in the finance department accessing a ERP server in the server VLAN. So what can we do? We can inject routes with higher priorities, or let's call it higher priorities for now, to redirect that traffic from the finance user to our malicious attacker-controlled PC. So that's pretty useful. Getting ERP traffic on your attacker machine could probably have some devastating impacts, right? In terms of FHRPs, what could happen over here? Again, we said there's a logical grouping with this priority, and then the higher priority becomes the active device in this logical group. So from an attacker's perspective, we can just assign a higher priority to ourselves, and then the user's traffic will be directed towards us, and then we would just forward that traffic onto the legitimate default gateway. Okay, so it's important to mention some of the challenges with these type of attacks. So you need to get specific. And what we mean by that is you need to inject more specific routes that's currently in the routing table. So you can join the routing table, observe some routes in there, and then if you observe that there's a /24 network, split that network into two, advertise 2 /25s, and that traffic is going to get redirected back to you. So that's all what we mean by saying be more specific. There are other things to consider, such as administrative distance and then the per protocol metric. For the purpose of this talk, we're just saying be more specific, and that's how we're going to beat the routing table. How did we do this initially? We were connected to a LAN, we opened up Wireshark, exactly how we shown, and we saw these vulnerable packets being unauthenticated, and we wanted to exploit it. So we started researching for some tools, and honestly, we were able to configure a virtual firewall in a quicker fashion than it was to get the existing tools up and running. So how did it look? Let's go through a demo and show you how you can do that with a virtual firewall. Okay, so on the left, we have a Wireshark capture running on the attacker machine, and you can see some OSPF hello packets. So at this point in time, you should get excited just seeing the packets, never mind like whether it's authed or not. It's a good sign already. On the right-hand side, we have our attacker FortiGate, which is essentially our rogue router or rogue firewall. And all that we have to do is match the parameters in the hello packet and configure them in the FortiGate, and then we'll become a routing neighbor. So you can see that there's no auth data, so it's going to be a really easy attack, no cracking required. Some other fields we need to take note of is the area ID, the hello interval, and the dead interval. So we're just going to match those parameters in the firewall, pretty simple, copy paste. So when we head over to the firewall section, we're going to configure a router ID. That's just our unique identifier within this process. We're going to add the area, which we observe to be as quad 0. And we're going to say on which interfaces do we want to send out our hello packets. And we're going to match the IP address displayed at the top URL bar. So only out this one interface. We need to add the interface as well. So you're going to give it a name. You're going to specify the interface on which we're sniffing, and we're going to put in the hello and the dead interval, which we observed on the left-hand side. Once we apply this configuration, you're going to see in the Wireshark there's going to be some OSPF conversation happening, and that's when the routing information is going to start sharing. So it should take a second, and you're going to see some movement in the Wireshark capture, and then you can see the LS update packets sharing the routing information. So it should take a couple of seconds, and then this state would have been processed, and both routers would have been shared the routing information. So let's give it a second, and let's see if the FortiGate had learned any new routes. There we go, we've learned a bunch of new routes. So pretty cool. We haven't really done anything malicious as such, but we've learned of new targets, and it's this more accurate way of enumerating targets. So Simon, what's bad about taking this approach?
So there are a few issues that we experienced when we took this initial approach. The very first is that you require access to such firmware, which is not easily available. And then you also require the knowledge of, first, what to look out for in the specific protocols, and then how to configure such a device, which is again not easily accessible. Then, with regards to the existing tooling, well, because they haven't been maintained, and because of that, they have dependency issues, which is just very tricky to get up and running. So we found the virtual firewall to be much easier than the existing tooling. But at that point, then we noticed that there is a recurring pattern over here in that we can easily extract data, or rather we can automate the process of extracting the important fields, then writing up a configuration for that, and take a legitimate virtual router and apply this configuration to that router, and in essence making it attack the network. So we wrote up a tool called Routopsy, which helps us achieve this, where it will first perform a packet capture, take that data, and then make the router kind of attack the network. And that's done using Python and Docker SDK with a few Docker containers and then some other extra bits to it. So with more specifically, we're using a FRR router, which we then weaponize with these configurations that we've got to perform these attacks. Some of the code, or rather the protocols, have code specific to it because they are Cisco proprietary, but others, such as your dynamic routing protocols, well, they've already been implemented in FRR. So we do not have to recode the entire protocol. The high-level overview of Routopsy is that it will first perform a scan, where it will perform a packet capture, taking these packets, and then extract the various information and build up a configuration. This configuration, it stops at this configuration. It does not go any further unless we tell it to attack. In the attack, it would spin up the virtual router and apply the configuration on top, which would then have it go and neighbor up. We can take it one step further because attack just neighbors up, where we can now inject routes. And so once we've supplied a route, this would just change the configuration in a small way, and that will now have the routes injected into the whole network, which Tyron will demonstrate.
Sure. So we're going to demonstrate learning new routes. Enumerating networks, I guess, is phase 1. Phase 2 is joining the routing neighbor, and then phase 3, adding some routes, which will eventually lead us in directing traffic to an attacker-controlled machine. So before we start off with the demo, let's get a quick lay of the land. We realize there's a lot going on the screen. That's why we're sort of giving a short briefing before we start running attacks. More specifically, the top left is our attacker's routing table. We're running a watch command on there, and as we perform our attacks, that routing table will update dynamically. On the top right, that's where we'll be running our Routopsy commands from, essentially our attacks. And like I mentioned, at the bottom left is the router, and at the bottom right, our victim. So let's start off with a demo. On the top right, we're going to perform our attack. And all you really need to take note of for now is that our IP address is 192.168.76.170. Just keep that in the back of your mind. It's not super important to remember throughout, but it's nice to have in the back of your mind. If we go to the bottom left, we look at our router, we take note of that IP address as well. You'll see later why these IP addresses matter. You can see that that IP address is 76.208. Also take note that we have 2 OSPF neighbors at this point in time. After our attacks, we'll have 3 neighbors. So we've mentioned there's the victim in the bottom right. The victim is doing some DNS queries and is connecting to an FTP server. And this is essentially the traffic that we want to modify. We're running a Wireshark on our attacker machine. We're filtering for FTP, and we're seeing that there's no traffic traversing through this FTP. And after our attack, we'll show the Wireshark again. So let's start the attack. Let's start off with the scan flag. And like Simon mentioned, this is just going to look for vulnerable packets, parse them, and then take the relevant parameters and push them into our config templates. So now you can see that we've detected vulnerable EIGRP and OSPF. And let's go look at what the configurations look for these, what these configurations look like for these protocols. So you can see we've parsed the autonomous system number 100, and we've included that into our config, root to EIGRP 100. Other than that, you can see in our network statement is our interface IP address that we showed initially. And all this is doing is it's ensuring that we're only sending these hello packets out of our specific interface, only our one interface and not a bunch of other ones. So it's pretty simple. Let's look at the OSPF configuration as well. It's a little bit more to take note of, but it's also pretty similar. You can take note that we've parsed the hello interval and the dead interval from the vulnerable packets, and we've included that into our config template. Again, our network statement includes our IP address. To reiterate, it's ensuring that we're only sending these hello packets out of this one interface. And you can see that we've also parsed the area ID from the PCAP and included that into the template. So at this point in time, nothing's happened. We haven't interfaced with the protocol. We haven't attacked anything. We haven't really achieved what we achieved with the FortiGate. So we could do that with our tool. You just simply substitute the attack flag with the scan flag with the attack flag. But that's a little bit boring. We want to meddle with traffic flows, and we want to inject and perform some redirection. So what do? We specify the inject and the redirect flags, and they work slightly differently. In terms of the config template, it's exactly the same, but the inject flag will forward traffic onto your default gateway, whereas the redirect flag will sort of make the traffic stop on your endpoint, which is useful for maybe a honeypotting scenario, or if you wanted to run a SOCAT and forward the traffic onto some other endpoint, or process it in whichever way you wanted to. So again, what's happened now is our inject and our redirect flags imply attack, which also implies scan. So it parsed those vulnerable packets, built config templates, but now it's deployed it into a container. And you can see some activity happening on the panes. So we'll explain what's happening. If we look at the bottom left pane, you'll see that there's some OSPF activity being logged from the router, saying loading to full, meaning that there's a state change in the router's OSPF. We've become a neighbor with that router, effectively doing what we did with the FortiGate. Other than that, in the top left pane, you can see our attacker machine is starting to make some changes, and you can see that the routes were automatically added to our attack machine. So this same thing that you saw in the FortiGate. We've learned routes. We now have new targets to go after. So more importantly, if you have a look at the victim, you can see that the victim's DNS query has changed to 1337, and the FTP trace route has gone from 3 hops to 4 hops. So we've successfully changed the traffic flow. I guess it's important to mention that you don't have to follow our templates. You don't have to use the inject and redirect. You can specify the attack flag, and then you can go perform your own type of attack should you be comfortable with a router interface. But nonetheless, let's have a look at what these flags do and what the template is that we've built for them. So on the top right pane, going from top to bottom, you'll see that we added static routes pointing to the null interface, and the IP addresses match the flags that we've specified. Then if we move over to our sort of host machine again, the root, and then you'll see there's static roots added to our host machine indicated with the asterisk, and that asterisk is saying that it's a null root. So at this point in time, you may be thinking, why are you guys adding things to the null interface? Because it's going to drop the traffic. We'll explain that now. So we still get that null root into OSPF, and how we do that is we specify the redistribute command. We can go verify on the router that those roots are within the OSPF process, and you can see there quad 8 and the 164 address is really within the OSPF process. We hop over back to our attacker machine, and we ask that question again. Okay, cool. We've advertised these roots into the routing process, but surely it's going to go to the null interface. How do we get around that? We apply some policy-based routing. So you'll see there's policy-based routing maps, and what we're doing there is we're saying if you match traffic on those parameters that we specify, forward it on to the next hop. But as I mentioned, it's only relevant for the inject flag and not so much for the redirect flag, as we're doing an additional IP tables rule in the back to NAT that traffic to your interface. So that's cool. We've neighbored up, we've injected some routes, but sort of what is the net result of that? Let's have a look. Let's log into that FTP again, or let's log into that FTP now, connect to it, specify the credentials, verify that we connected, and switch back to the Wireshark to see if we can successfully man in the middle. So here you can see that we've man in the middle, or person in the middle, I apologize, the FTP tracker, and we can observe the username and the password. So there's quite a bit that was going on over there, and we'd just like to reiterate what happened over there. We learned some new routes, just like with the FortiGate, but we went a step further and we injected some routes, and that resulted in some traffic being redirected to our attacker-controlled machine. Simon, is there a way for us to manipulate traffic coming inbound to our local subnet?
Yeah, there is. Using dynamic routing protocols, we can have the traffic, using dynamic routing protocols, we can insert a route to a host on a local LAN segment and inject that into the routing process of the greater network, and thereby having traffic that is initially destined to that host to first come through the attacker host before the server. So if we take a look at the diagram right now, the victim would attempt to access the server and would follow the blue arrows. But now, during this attack, we would take this route of the server and tell the routing process, hey, we know a more direct route to that server, and that would then allow us to capture traffic from the victim destined towards the server, and then we can manipulate it to whichever way we would like to. How we achieve that? Well, we first have to take a closer look at the attacker host, the configuration within it. There are two containers, or rather two routers in there, one regarded as or known as Routopsy and the other as the peer router. Routopsy will neighbor up with both the external router as well as the peer router on the host. The peer router is there mostly just to inject the route into the larger routing process, but Routopsy has some configuration within it to prevent that routing, or rather that route, to be added to its routing table. And why we want to prevent it is because Routopsy shares the routing table of the attacker host. So when this traffic comes back from another network to us, we would like to then manipulate it to whichever way we want to. And so that's why we need to is prevent the addition of that route into our table. Let's take a look at the demo and how this is done. We're first going to orientate you in the layout of this demo. In the top left is the attacker window. In the top right is where the attacker will be performing their commands. And in the bottom right is the victim. As you'll see, the top left right now, the routing table is quite normal. This is without us peering up. In the top right, we're running netcreds. And then we're going to show you that the victim's traffic is right now not being captured in any way. This just shows that we haven't done yet the attack, and that the victim is able to normally access the SMB share without its traffic being tampered anyway. So you'll notice now we're attempting to connect to an SMB share. We're going to enter in our password, and then we're going to do a directory listing. While that's happening, you'll notice that there is no data that is being printed out by netcreds. That just proves that right now the victim's traffic is going the normal blue line way, the blue arrow way. If we now write up the command to run Routopsy and target the protocol OSPF, This will first scan for a vulnerable OSPF configuration, then it will create the necessary OSPF config files for the virtual router, and it will spin them up. So you're going to notice now that it spins up a peer, and it will spin up Routopsy. Let's take a closer look at the configuration of the peer. Within the peer, you'll take note of first the OSP, or rather the routes, the static routes we're injecting. And that is the static route to the server, the target server. All right. Then next is the OSPF process. Within the OSPF process, this tells it to neighbor up with Routopsy and also redistribute the static routes. This is how we get that route into that larger routing process. We're now going to look at the configuration of Routopsy and how we prevent that route from being added to our routing table because it shares the routing table of the attacker host. The first two statements are the network statements for it to neighbor up with the external router and the internal peer router. The next two statements are access lists. The very first access list is for 192.168.76.216/32. So any packets with that route will match that access list. And then there's a second access list for anything else. Together with the route maps beneath it, we're able to control whether this route is added or not added to routing table. We take it one step further because we're using OSPF to neighbor up, that we now add these route maps on top of OSPF so that we don't learn this route and add it into our routing table because, again, it's shared with the attacker, but it is propagated throughout the larger routing process. So now that we've got that down, we're going to have a look at how we've managed to redirect the traffic. Right, so we're going to run netcreds, and then we're going to go back down to the victim and attempt to connect to that same SMB shared. Now once I've entered the password in, you'll notice that netcreds will print out a netentl hash. This means we've successfully managed to redirect the traffic of that victim. So now we've shown you how to, using dynamic routing protocols, inject traffic, or rather inject a route to a host on the local LAN segment into the routing process, which then has traffic originating from another network first go to the attacker before going to the server, allowing us to perform a person-in-the-middle attack. But Routopsy doesn't only perform DRP-related attacks, we also perform attacks against first-hop redundancy protocols. And we'll show you a demonstration against HSRP. First, let's orientate you around this demo, or the layout of this demo. In the top left is the attacker window. In the bottom left is the victim router, or the vulnerable router rather, and on the right side is the victim attempting to reach quad 8 via trace route. Take note that the trace route to quad 8 takes 17 hops, and this will change after our attack, showing that we are performing a person-in-the-middle attack. If we go back to the top left window where the attacker sits, you'll notice that the IP address is 10.20.33. Take note of that because that will be the next active after the successful attack. So we're going to target the protocol HSRP using Routopsy, which will first run and perform a scan to determine whether there are vulnerable HSRP configurations. Once it notices that, it will start sending out HSRP hello packets with a much higher priority to allow us to become the active default gateway. You'll notice that in the bottom left, where the vulnerable router sits, that it goes from a standby state, or rather an active state, to a speak state, and from a speak state to a standby state, meaning an election process had gone, and that there's a new active router or a new default gateway which has a much higher priority than itself. If we look at the active, it is right now 10.20.33. If we take a look at the victim, it now takes 17 hops, but now it takes 18 hops to reach quad 8, with the first hop being 10.20.33. So we've successfully performed a person-in-the-middle attack via first-hop redundancy protocols. Great. So you could run Routopsy to do this, and then you'll notice that maybe your network interface is melting away because you have the entire user range going through that one laptop. And you may have realized, oh wait, I forgot to turn on IP forwarding. Well, we've got safeguards within Routopsy to prevent that happen, but what you should take note of is that attacks against first hop redundancy protocols as well as dynamic routing protocols may cause denial of service. These can be fixed. And going back to what Tara mentioned earlier about being specific with attacks, we can be specific with our configurations. Rather than being minimal and leaking out these packets to all networks, only speak these specific packets, or rather, speak these specific packets on specific networks where you have another router, where you may need to perform routing protocols or dynamic routing protocols, or where you require high availability between two default gateways, between two gateways. We can take it further and add stronger authentication by making use of crypto and a much stronger password such that an attacker is not able to crack it. We can also then add on top of first hop redundancy protocols, making use of a much higher priority, such as the maximum value, such that no one else can come into the network with a default gateway with a much higher priority value. We can also attempt to perform blue team or detection against these attacks by collecting syslogs of the various network devices and monitoring for state changes, monitoring for new neighbors on a dynamic routing protocol, or monitoring for a new active on a first hop redundancy protocols. But if you're a skilled attacker, you may probably want to just redirect that traffic elsewhere. Tyron, do you want to introduce them to the playground?
Sure thing. So we realized that everybody doesn't have networking kit lying around, or maybe they don't have the know-how to configure a network emulator to sort of build a vulnerable network to test these attacks and play with these vulnerabilities. So what we've done is we've built two YAML files which you can run with Docker Compose, and in the DRP file, it spins up a router, it spins up a victim and our Routopsy machine, and there's two networks. And if you perform the attacks, you'll see the traffic traversing from the one network to the other network, which is observable by Routopsy. And in the FHRP lab or mini lab, there's a victim and there's sort of a high availability default gateway configured with VRRP. It's configured insecurely. Routopsy can see that traffic, and then you can take advantage of that, effectively redirecting the traffic from the victim to Routopsy, which will then forward it onto the legitimate default gateway. What we want you to take away from this talk is that network protocol security is still very important, and using our tool, it's possible to meaningfully show impact. And it's also agreeing to or speaking towards what Simon has said. It's quite easy to secure these things, and it's also possible to detect whether there's some malicious activity going on. And before we end off, Simon would like to show you what we're currently working on.
So picture a Kubernetes cluster with one master and two nodes. This Kubernetes cluster has Calico configured, which makes use of BGP to share routing information between the various nodes within this cluster. And then that one node has been compromised through some means, say a pod and privilege escalation, or an attacker had access to the internal network and was able to guess the password root. The victim node has a pod that has been deployed to it, and that performs, when performing DNS queries, follows the traffic denoted by the blue arrows. Should we have compromised this node, we could maybe use bird controller to start messing with the routing table, but not everyone is familiar with the bird controller. And so we've come up with a little tool that helps you either mess with the routing tables of all the nodes in a cluster or for a specific node within a cluster. And so we can actually have that traffic redirected following the red lines that we've shown. Rather than going to the master for DNS, it would come to us. Let's show you how that is done with a demo. Let's first orientate. In the bottom left is the master. In the bottom right is node number 2, the victim. And in the top is the attacker node. In the bottom left, the master, we're showing you guys the core DNS with the IP address of 10.96.76.3 and 10.96.76.2. Those are the routes that we're going to want to inject, as we want that traffic to come to us. The next thing that we will take note of is the pods deployed. There is a DNS utils pod deployed to node 2. Let's attempt to resolve the Kubernetes name within that pod, and we receive an answer 10.96.0.1. If we go and take a look at the routing table of node 2, keep an eye on that, because that will change once we've injected new routes. Going to the master, we're going to run the script. which will inject those 2 new routes, and you'll notice that node 2's routing table has now changed. So we may be able to get the traffic now to come to us. Let's see if that is the case. Let's go back to the master node and attempt to resolve Kubernetes. And now we have an answer of 1337. So we've effectively redirected traffic from that node. Thank you guys for joining us in this talk. You guys can find our talk, well, our code published on GitHub SensePost Routopsy right after we're done with here. And you can catch us on the Twitters or on email.
Thank you very much.
Hello.
Hello, everybody.
Hope everyone enjoyed the talk.
Yeah, I hope you guys enjoyed. I think we can answer the last question first because we tried to sort of answer most of them in the chat. The last one was, I may have missed it, but the playground YAML is for what platform container? Sort of, both of them are slightly different, but the attacker container will always be well, for the DRP stuff, it will be a FR routing container. And for the FHRP, the VRRP is just a custom keep alive D container, which we perform the attack with. I don't know if that answers the question.
Then the other question, does this tool work in an AWS VPC or Azure VNet? Just to get some more clarity around that, the tool Routopsy was mostly done on on-prem kind of infrastructure and setups. So that's something we still have to go and play around and see what the networking is like within the cloud on that side of things. And I'm just checking if there's any other questions. I believe we've covered everything else. Regarding the tool, we'll just now go onto GitHub and be releasing it live so that everyone can go and have a look at it and play around with it and also open up pull requests for us, right?
Yeah, and there'll be a blog post in not too far future at some point.
Thanks everyone for joining.